This is the last set of topics in this particular unit, and we will just summarize some of the issues. Um, the methods, Boolean, vector space, and probabilistic, they are all relatively, I would say vector space, and they're all slightly similar. The vector space is related to probability, because if you define the components of your vector in a sophisticated fashion, like TF, IDF, and more, and add in effects of page rank and things like that, you're going to get a probabilistic version of vector space model. So the Boolean model is really not terribly interesting because it's a 0-1 model, and so I would say that's you will not ever use that. You will use some variant of the probabilistic / vector space model, namely vectors with probabilities. And although the probabilistic model may be best in principle, at least in practice, is essentially applied through the vector space idea by using sophisticated components, and that vector space version of the probabilistic model is a good way, and you cannot, there's no easy way of generating probabilities except in a fashion like that. There are obviously a lot of other important issues, such as ambiguity. We want, when we have Jordan, do we want the Kingdom of Jordan, or the river called Jordan, or the basketball player called Jordan? And we need to get diversity. And if we don't know from some other context information about the person doing the query, maybe the person is in his profile that said he's a basketball fan, that would tend to make us want to return Michael Jordan matches more often than Jordan River matches. Another important issue is synonymous words. Elevator in the US is the same as lift in the United Kingdom. Movie and film roughly mean the same thing. And when you have very short queries, you have to know what's going on. So when I type a one-word query, I'm often just trying to spell the word or just verify the dictionary definition of the word. So these are all part of information retrieval, and as far as I can see, the current search engines do such a good job in this type of thing that it's not so clear that there is so much more work to be done here. Well, we have some data on the size of the web and following slides. Actually, from the data I have, it isn't actually doubling in size every 2 years. I think it may have stabilized. And as well as what you know, there are, of course, as I pointed out, the deep web, the things hidden behind databases, which is not so easy for the search engine to find out, because the search engine doesn't quite know what queries the databases need to be given to reveal all the information they have. So, and of course, there is, we know, more and more importance with different media. The number of videos and images going up on the internet is growing fast. That's growing much faster than the number of text going on the web, because people have only through social networking started putting a lot of photos on the web. And of course, this goes on around the world in lots of different languages and things like that. So here's a picture from the worldwidewebsize.com, which estimates the size of the web by doing simple queries to Google or Bing. This is the Google results. Bing results are somewhat smaller, and see what documents or how many documents are returned. And then it uses an estimate, which you can do, that if a certain query only occurs in a certain fraction of the documents. So if you can just correct that number that Google or Bing gives back and get you the total size of the web. And so you can actually see, according to this, the web's around 45 million over the last 2 years and has not changed, as measured by Google. And there seems no special reason why, to me at least, why Google would stop doing this. There's a little few glitches here. That's when this particular site did not measure the size of the web. They had some gaps in their measurement. Maybe their computer went down. We already pointed out at the start of the previous lesson the web is a graph. We've emphasized that in PageRank, and we will come back to that with particular graphs when we find PageRank in the software lesson later on. And there are all sorts of things you can study, the number of people pointing at a number of pages pointing at a given page, the number of pages that a given page points to, the number of pages on a particular site, and what the connectivity is, and how all this happened and how it's evolving. So we actually discussed that right at the beginning of the previous lecture, and we gave you this bow tie structure. We have a whole bunch of sites with links starting then these sites and going to other sites, in particular to the core, which are just interlinked sites here. And then we have sites which are mainly pointed to and don't tend to do a lot of pointing out. These are very informational sites. They're not trying to take you anywhere. These are sites that tend to take you places. Hubs will be a very good example there. Authorities would sort of probably be here because authorities would tend to link to lots of other things because they would tell you everything about the field. However, other sites would just have end information and not try to point to many other places. And we have disconnected components without significant connection to other sites. And then we have various sort of glitches and sort of dendrites sticking out of this basic bow tie. So this stuff here is meant to be less than 10%. All right, here we have some two graphs that we showed actually at the beginning of the last lecture, at the same time as the bow tie picture. They show on the left we have the number of links going into a page, and so like this would say that we have 1,000 pages, and this sample have hyperlinks which are have around 70 hyperlinks going into them, and this is the link of the hyperlinks, and this is actually the link of the users browsing the web, and here's the number of links going out, and you can see apart from the falling off, which is for basically links less than or equal to about 10, then you get a slightly strange structure, but for once you get above 10, they do fall off roughly with straight lines. And a straight line means that there's a power law, namely the number of pages is proportional to the in degree or the out degree to the minus the exponent. So this is they're roughly going like 1 over the degree squared. So if you that means if you double the degree, a quarter as many pages have that degree. So power laws are very common in complex systems.